Alright, welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is section 8.3, which deals with the names and formulas for ionic compounds. The objectives of this lesson is to write formulas for ionic compounds and oxyanions, and name ionic compounds and oxyanions. Alright, so we start out here talking about formulas for ionic compounds, and we need to talk about this topic of a formula unit. And so it's the simplest ratio of ions in an ionic compound. The other thing that we have to take in mind or take into consideration is that a compound will have a charge of 0. So that means the total positive charge will cancel out the total negative charge. And there's going to be a shortcut method that I'm going to show you how to use, so just pay attention here to notes. Our examples here from what we have here is KBr, or potassium bromide, which shows that there is 1 potassium for every 1 bromine. Okay? Now, magnesium chloride shows that there's 1 magnesium for every 2 chlorides. These things, these little small numbers down below here, are your subscripts. Now, if no subscript is written, we assume that we have our value of 1. So magnesium, no subscript, value of 1. All right, so we move on here to determining what we have or what we have to work with. So the first thing, the simplest type of ionic compound is going to be a binary compound. And so the compound is going to be composed of 2 different elements, each having a different charge. So you're going to have a cation, the positively charged ion, and a negative ion called the anion. And again, an example is magnesium bromide. And you can see here, there's just 2 different elements in a binary compound. Now, a monatomic ion is a 1-atom ion. So magnesium is 1 type of ion, and so that would be a monoatomic ion. Okay? What we can do here is this. A monoatomic ion, we can find the charge using the periodic table. Now, we did this in section 2, but I want to reiterate this again with our groups having a distinct charge. So group 1 will always have a charge of +1. Group 2 will always have a charge of +2. We skip the transition metals and we move to group 13, has a charge of +3 when it forms an ion. And then the group with carbon, we have the transition here to a plus or minus 4. The charge of nitrogen's group would be -3. Oxygen's group would be -2. And then we would have -1. Now, remember from our last section, I blew this up on a bigger periodic table. So if you want to see that blown up again here, we will utilize this in the next few slides. So keep that handy that we have here and present. But I wrote that here. It's very small, and it's written in this section here. You can add it to your periodic table. All right, so let's keep going here, and let's talk about the oxidation number. So the oxidation number is simply the charge of that ion. This is equal to the electrons transferred in our particular element, okay? So what it's also used for is going to be used for making our correct formulas for ionic compounds. So let's take an example here, and this example is the formation of sodium chloride. So what happens here is this. Our sodium has 1 valence electron. Remember, sodium is in group 1, and it has 1 valence electron, so I'm going to represent that with 1 single red dot. Now, chloride is going to have the symbol Cl, and it's going to have 7 valence electrons. And I'm going to represent those 7 valence electrons via blue dots. So what happens here is this. Our one red dot gets transferred to chlorine. So when a formation, or when sodium chloride is formed, we have this. Sodium gets rid of 1 electron and becomes positive of 1 charge. Chlorine gets that electron from sodium, and it gains that electron. And so I'm going to draw, again, the electron that it got from sodium is that red one, and it has a -1 charge. So again, they form those charges that we just wrote on the periodic table because an electron is transferred or taken by one element or another. So let's go ahead, let's get into details for how we write our ionic formulas. So our ionic formulas is this. We always put the cation, or the positive ion, first. Then comes the anion, or the negative ion, second. The next thing we have to worry about is subscripts. So these are those small numbers to the right of our elements with our symbols. So they are used to represent the total number of ions present in the ionic compound. However, if there's no subscript written, that subscript is assumed to be 1. So our example here is this. Determine the correct formula for the ionic compound formed between potassium and oxygen. So the first thing that I'm going to do here is I'm going to look up potassium, and I want the symbol for potassium. All right, well, I find it. The symbol is K for potassium, and I'm going to keep that periodic table handy because we're going to need it. And the next thing is I'm going to write our O for our oxygen. Again, O, capital O, represents the symbol for oxygen. Now what I'm going to do is this. I'm going to find potassium on my periodic table, and I'm going to go up, and I'm going to recognize it's in group 1, and it has a +1 charge. So what I'm going to write is this. I'm going to write a 1+ charge to represent that charge of potassium. And over here for oxygen, if we go, we find oxygen, we go up all the way to find its charge in its group. It has a -2 charge. So I'm going to write 2-. Now, remember, we want the charges to cancel out. So a simple way to write our formula is this. We're going to take the charge number from our opposite ion. So in this case, it's a 2 from our oxygen. And I'm going to draw an arrow, and that becomes our subscript. Okay? So we write K. And I'm going to represent this in blue because that blue number came from our charge of oxygen. And then we do the same thing here. We do the same thing with our charge for our potassium. Okay? So the charge number comes over here, and we write that as a 1. Now, I'm going to do this just for this example here. But the 1 is not written, okay? So when we would actually write the formula, we would not write that 1. And so for the formula for ions between potassium and oxygen would be K2O. Now, again, I'm going to represent that we have blue for that charge number. That's where we got that from oxygen. So we'd have K2O. And that would be the formula between a potassium and oxide ion, okay? So let's keep going, and let's talk a little bit about polyatomic ions. So polyatomic ions are ions that are made up of more than one atom. So something unique to polyatomic ions is that they are a set group. And so because they are a set group, the entire group gets that charge. What that means is we cannot adjust that formula of those polyatomic ions. Okay? Now, the subscripts of the polyatomic ion cannot be changed. So if we need multiple of that polyatomic ion, we need a set of parentheses. Now, what's really nice here is I provide two charts that you can utilize on any assignment or exam, and they have both the name and the formula of our particular polyatomic ions. So the first chart here breaks the ions down by charge, and a polyatomic ion here, if we check out the 2-, carbonate has the formula CO3, and it has a 2- charge. Over here, phosphate has a PO4 as the formula and a 3- charge. Again, this chart is very useful if you're looking polyatomic ions up by their charge. There are some ions that we need to utilize this other sheet. Now, this sheet also breaks it down by their charge, and then it lists them in alphabetical order. So we'll utilize this here in a second. So our example here, it says the ionic compound formed from the calcium ion and the phosphate ion is a common ingredient fertilizer. We want to write the formula for this compound. So the first thing that we're going to do is we're going to look up and we're going to say calcium. Now, we should be familiar with the periodic table. That is a single element on the periodic table. So I'm going to do one thing first. I'm going to write down the symbol for calcium, which is Ca. So we get Ca. And then I'm going to take a look for Ca. You go up. You find the charge in that group. It is a +2. So I'm going to write it as 2+. That's how we write it. And then phosphate. I'm going to tell you for this example, that is our polyatomic ion. So I'm going to use this chart here. I like using this chart. It's a little bit nicer in my opinion. And I'm going to look for phosphate. So I'm just going to scan. Oh, found phosphate. Phosphate has the formula PO4. So phosphate has the formula PO4. That phosphate has a 3- charge. It's in the 3- column. It has a 3- charge. So phosphate is 3-. Now we have a couple of things. We need to write the chemical formula. So what we do, we take the charge of the opposite ion. So I'm going to start here with the charge of phosphate, 3-. And I'm going to draw an arrow, and that 3 is going to represent our subscript. So I'm going to have Ca, and I'm going to represent that in blue, so we identify where that's coming from. So we have Ca3, and then we do a similar thing. So we bring the 2 over, and that 2 tells us we need 2 PO4s. Now, what we have to do is this. PO4 has to stay in a chunk, but we need 2 of them. So what we do, we first start out with a set of parentheses, and we put PO4 to say, hey, we're working with PO4, and it's a phosphate polyatomic ion. And then we come around here with our number of phosphates we need, which was 2, and we write down 2. The last thing that we do, we look at just the subscripts written in blue and red here, and we ask ourselves, can we simplify? The answer to that is no. So our formula for a calcium ion and a phosphate ion is Ca3PO4 2, and that would become our answer. All right, so now we need to shift gears and we need to go from formula writing to naming ionic compounds, okay? So, naming ionic compounds, we have a series and set of rules. Rule number 1, we name the cation, the positive ion, first. Then we name the anion. So just how the formula is written, we have to go positive first, negative second. For the cation, we utilize the element name if it's a single element. So Na, if we would go to name Na, if we found that in our formula, we would take a look on the periodic table and we would find, all right, all we need to do is write down the name exactly as it is on the periodic table. And the name of Na is sodium. So we would just write down sodium. Now, what we have to check for our cation is if it's a single transition element. So we always have to double check if it's a transition element. If we do, the charge must be indicated in parentheses. So this will be a transition element. So we have Fe. We always double check if it's in our transition elements. If it's in our transition elements, we have to write the charge. We start by writing the element name. So Fe, the element name is iron. And then we indicate the positive charge of that transition element in parentheses, and we utilize Roman numerals, okay? So because there's a 3 plus charge, we have iron 3, and we would represent that through the Roman numeral 3, which, remember, the Roman numeral 3 looks like 3 pillars followed by that I, so that would be iron 3, and that indicates a 3 plus charge. Now, just so you know, Roman numerals, I means the number 1, 2 I's mean the number 2, 3 I's represent the number 3, and kind of the weird one, the oddball here, a 4 is an IV. Okay, we really don't go much past 4. You'll see it sometimes, but in this class we'll stay pretty much at 4. The next thing here is this, naming the anion, the negative ion. If it's a single element, we keep the root of the name. And so what I do is this. I just look up Cl, and that's our example, and I write down the entire name on the periodic table. So I write down the entire name of the periodic table, so chlorine. And then it says here the ending changes. And I will tell you that the ending is slightly changed for each and every element. There's no systematic way. It's how it's pronounced and things of that nature is how they change it. But it changes to IDE. So when we would write the name of Cl here, we would get chloride. And I'm going to represent the changed ending in red there. So Cl would be chloride. All right. Now, we get down here to polyatomic ions. Polyatomic ions, all we do is we just name it the way we see it on a sheet. So we look up NH4 with a 1 plus. Well, NH4 with a 1 plus is ammonium. So all we do is we just copy it directly from that sheet. So the name here of NH4 plus would just be ammonium. Now, a negative polyatomic ion, we would do the same thing. We would look it up, and so we find OH1 minus. Well, OH1 minus has the name hydroxide. We copy that name directly down. All right, so now we got our rules. Keep those handy. They may be useful as we go through our last set of examples. I'd also keep that periodic table and the ion formula sheet handy as well. Okay, so we got the rules. Now, what I've provided you before we turn to our last examples is this. This is a flow chart of everything that we've talked about. So sometimes it's really helpful when we are naming ionic compounds to have a guide path of how to go through the process. So number one, we're going to determine the cation and the anion of the given formula. Number two, we're going to ask ourselves, does the cation have only one oxidation number, aka is it a transition metal? So you could put, is it a transition metal? If it is a transition metal, we are going to follow this path and answer that question as a no, and we're going to write the name of that metal with the charge indicated in parentheses. If there is only one oxidation number, we simply just write the name. All right, so this is just another method to help you understand how we get our formulas. All right, so let's turn to our examples, and this will be our final part of section 3. All right, so our values here, what we have here, the first thing we have NaBr. So what I like to do is this. I like to come in and separate the positive from the negative ion. Well, what's nice about having a binary compound is they split right down the middle. So I start with Na, and I turn to my periodic table, and I look for Na. Oh, it's right here. The name is sodium. So I start out by just writing down, okay, I have sodium. And then I ask myself, before I leave sodium, is sodium a transition metal? No, it's not found in this block of 10. So that means I don't need to indicate the charge. Then we have Br. I look up Br. The name of Br is bromine. And initially, all I'm going to do is I'm going to write down that name, bromine. And then the rules told me, hey, the second thing listed, we had to change the ending. So the ending can't be bromine. It has to be bromide, IDE. So when I write the name of the ionic compound, the name of NaBr would be sodium bromide. And that would be the name. All right, so KOH. Now, again, the hardest part initially is going to be identifying what is positive from what is negative. What is positive here, the only thing positive is our K, and so it's going to split right here between K and OH. So what I'm going to do, I'm going to turn the periodic table. I'm going to find K. The name of K is potassium. I write that down exactly how I see that on the periodic table. Now, OH, identify here or see how we have OH. That is a polyatomic ion. So you're going to have to use your sheet, but we find OH, and OH is right here. And for a polyatomic ion, all we do is we write the name exactly as we see. So for hydroxide, that is OH, and we do nothing besides copy the name of that particular polyatomic ion. All right, so now we piece this all together. There is no name changing in because OH is a polyatomic ion. So the name of KOH would be potassium hydroxide. All right. Keep moving on here. CuNO32. All right, the nice thing about parentheses is it tells us where to divide. So we're going to divide right here. So Cu, I look it up on the periodic table, okay? Cu is right here. The name of that is copper. And I'm going to come back to this momentarily. So I'm going to write down copper. And I ask myself, is it a transition metal? Yeah, it's in that box of 10 transition metals. So what I have to do is I have to put the charge in parentheses. I'm going to leave that blank for right now. And then I'm going to turn to NO3. Okay, NO3, like I said, it's all in a chunk or it's all in a block, so you know it's polyatomic. So you're going to have to turn to this sheet here. So NO3, I'm going to look. I know it's negative. And NO3 right here, the name of that polyatomic ion is nitrate. So NO3 is nitrate. Now we get to this. One, because NO3 is a polyatomic ion, we do not have to change any name or any ending. But we get to this business here with the charge, okay? So now we have to do a little math. So what we're going to do, we're going to break down the formula. And so we're going to start with Cu. I'm going to put Cu, and then I'm going to put a times symbol by how many Cus I have in my formula. Well, there's no subscript written, so that means there's one Cu. Then I'm going to say plus the charge of NO3 minus. So NO3 minus, if I look this up, NO3 has a 1 minus charge. So I'm going to put -1 times the number of nitrates I have. So I'm going to say times 2. So again, -1 is the charge of the nitrate ion. 2 is that subscript, how many nitrates we have. Remember from notes, we said that a compound, an ionic compound, must add up to a total charge of 0. Okay? So now, I'm going to consolidate this. So Cu times 1 becomes just Cu. And then -2 times 2 would be a -2. So I'm going to say plus a -2 equals 0. Now, we solve for Cu, or we get Cu by itself by adding 2 to both sides. And so the charge for copper here becomes a +2. So we indicate this with a set or a Roman numeral of 2. So we went through all that business to identify the correct formula here. Now, CuNO32 would have the formula of copper to nitrate. Okay? So that would be our name here. Now, Ag2CrO4. Okay? Well, again, we have to identify where is our split from our cation to our anion. So if we get familiar here with our polyatomic ion sheet, this will start to become a little bit easier. I'm going to give this one away here in notes, but you're going to split between Ag and CrO4. So we start out here with Ag. We look it up on the periodic table. Ag has the name silver. I keep that handy because I always have to ask myself, if it's a single element listed first, is it a transition element? Well, yes, Ag is a transition element. So, under most circumstances, we would have to put that in parentheses. However, and I want you to write this note, silver and zinc are two exceptions to this. So, silver and zinc always have the same oxidation number, and I want you to put under oxidation number the same charge, okay? So oxidation, for us, we're going to call that the same charge. And so anytime we have a silver, silver is always going to have an Ag1 plus. Zinc, if we ever run into zinc, which we will, is always going to have a 2 plus. So what that means is no parentheses to indicate charge is needed. So that's really nice. We can avoid a step here. Again, that's only for silver and zinc. All other transition metals, we have to abide by that set of parentheses. All right, so now we get to CrO4. It's polyatomic, which makes it real nice because CrO4 is chromate. So all we got to do is write down what is on that sheet. So we look up here and we have chromate. And so for Ag2CrO4, this becomes silver chromate. All right, we went through quite a number of our examples here in this section. This is a really important section to remember because we'll utilize it throughout this particular course. Hope you have enjoyed this particular episode. And as always, if you have not done so already, make sure you subscribe.